clustering, okay? Okay, I think you guys can see the slides all right, so we'll go ahead. If you can't, just holler out on chat. I think we'll be able to see that. So the idea behind dimensionality reduction you're already, I think, very familiar with is the fact that when we have very large data, especially if we want to use something like a traditional machine learning algorithm, rather than a neural network or other type of network or learner that can overfit easily, then we may need to comb down a number of features that we're working with. Okay, so we can do that so that we have an easier time learning. We have fewer parameters to worry about. Um, but there's also the idea that we can get something that is easier for us to understand as humans, as we've seen before. You know, the idea that a high dimensionality data is really, really difficult to visualize and learn from, and pull together understanding from different parts of the data set, especially if it's categorical. For image data, it's sometimes very hard to use something like dimensionality reduction to favor useful features, right? Okay. So let's see, we had a chat. Just check whether we have anything. When we say easier learning, does it mean better? No, not necessarily. It can mean better. It can mean faster in terms of how long it takes us to learn a particular algorithm to come out. Usually, we can reduce some noise in the data set by using dimensionality reduction techniques. But not necessarily any better. Okay, it's sometimes we do get better results. It depends on the particular learner. As you may have noticed, some of the learners are pretty sensitive to noise, and if we think that the features that we have provided the learner are noisy, sometimes dimensionality reduction is helps to mitigate that problem. So I hope that answers your question, Qinghai, about that. Okay, let me pull that up again. Sorry. Okay, and Kok Jun asks, can we check whether the topics before recess week will be tested for the final? No, they won't be tested except for one, okay? And the one that's being tested is regularization and validation, because we did not actually touch upon that when we were doing the first exam. Okay, oops, I think I skipped a little bit. Okay, so hopefully that answers your question on that part. Okay, but again, keep on telling us if it's not. Okay, yeah, it's exam 2. It's not a final exam. So we covered the first half, and you know, some of the basic concepts, of course, you'll need to know, like the idea of bias and variance, you know, is a key tenet of machine learning. And even though we've tested it already in exam 1, it's not to say it won't surface itself in exam 2, not in the sense that it's an examinable topic, but it will be some of the things that you'll have to reflect on, because of course that's you know, a basic underpinning of machine learning. So when you go to exam 2, we hope you understand that concept and can apply it in analyzing some of the algorithms. Okay, so we're not going to directly test you on it because you've already had it, and exam 1 already covered it, but you know, having an understanding of it will be very helpful for exam 2. Okay, so there are lots of cases where dimensionality reduction would be helpful, right? So think about stock market data, right? So there are inherent structure in that data set. There are sectors that move together, and then having some way of representing those sectors, even though it's not explicitly stated in the data, would be helpful. So if the dimensionality reduction algorithm notices a couple different stocks are moving together, it might represent it as a single variable, and then try to code using other dimensions variance from that. Okay, so the first idea is like we have a data set. So we have something like this, right? This data set here. Okay, and it's represented by a number of points, and those points are given to us with, okay, with 2 dimensions, right? And so what we want to do is try to express this in a better way, okay? In a way that we can use fewer dimensions instead of the entire dimensional space, right? So here it's a toy example. We only have two features, x1 and x2. And what we want to do is figure out some way of changing it without using any information about the label. So again, you can see all the data points here are blue, so they're not labeled with a particular Y label here. So they're just data points in the X dimensional space, okay? And what we want to do is project it into a new dimensional space where we can use, again, fewer dimensions, okay? So the first thing we were going to notice is that we can take the data and try to represent the direction of most variance. So if we look at this data set, it's somewhat oval in appearance, right? So we would want to say what dimension has the most variance for the data set, right? So we can try to engineer that by looking for orthonormal or orthogonal basis for different two different dimensions, again, taking the x1 and x2 as a linear combination so that we can express the data set in some way, okay? So we have the original x1 and x2, right? And then we're going to try to find a z dimension, okay, which is listed here, okay, in such a way that we can capture most of the information about the points using just the z1 dimension, okay? So the Z1 is then basically a vector that you can encode X1 and X2, okay, by notions of a component in X1. So we have, let's say, this part here, which would be V1, and then this part here, which would be V2, okay, and expressing that as a sum of those two individual original vectors to create the composite one. Okay, so that's the idea behind it, is that we would have this dimension that we need to figure out. Okay, so it's not particularly hard to do. What we have is a set of points, right? Okay, let's see. So why is Z1 the same for all points? There is a problem here. I think this thing should actually be over the V, okay? So it means that the vector for this direction is the same, okay? Not for Z1, so it should be over for that one there. So thanks, Li Shuo, for noting that. Okay, so we'll get that corrected later. I think there were at least one other student pointed out the error in the lecture notes for that. Okay, so with this understanding, as long as we decide where V is, okay, and a direction of between this, we can do all of the rest of the work, right? So we have a set of 2D points, okay? And once we decide where V is, we're gonna get one-dimensional points along this V axis, right? So we know Z1, so let's say this is point 1 here, okay? Then we know where Z1 is, right? So this is Z1 just for this segment here, okay? And we're gonna do the same thing for all of the other points. So let's say this is point N, then this entire segment here would be Zn, right? So we're trying to encode as much data as possible where the variance on this direction is the largest, okay? So the reference point could be anywhere on V. We're just choosing one here. Okay, of course, when we do this projection, we're losing some information because basically what we have are just these data points here, right? All the data points on this line. We don't have any information about the offset of the line, so we've just projected it on this line segment. Okay, so we need to shift the data so that the sum of squares is lessened, right? So we're going to actually pick up the line and then move it a little bit so that we can represent it so that the line segments lose as little data as possible, okay? So basically we just shift it from the origin so that we can do this, okay? Right, so the closest line that separates that best encodes all of the points will obviously have to pass through the center of the points, okay? So we have that observation. So we can reconstruct it as best as possible by projecting on the line V, right, on this V that's transposed over here, okay? And then adding back the mean of all of the points, right? So when we do that, then we have the reconstructed point that's here, okay? So that's the reconstruction of these points so far that we have for that particular item, right? So we'll get the reconstructed points actually on the line, okay, at this point because we haven't encoded the other dimension yet, okay? So we've done that to try to lower the dimensionality of the data set. So we're ending up with this data set when we're projecting on V with only a single dimension of just points on this one line segment, right, on this one dimension, where we've decided V as a way of lowering, representing as much of the variance of the data in the particular data set, okay, by first finding the direction of largest variance and then translating the coordinates of the center from the origin, right, from the origin over here to a new origin, which is the mean of all of the x's, okay? So that's the idea. Okay, so it says the procedure down at the bottom, right? First, we're going to transform to a new coordinate system, right? And move the origin to the new place, right? So we've done that in the top diagram, okay? And then drop any unimportant directions, or at least the ones where we want to lower the amount of data that we're transmitting, okay? So we might throw away V2, so this dimension over here, we're just going to discard, okay? And then we'll have everything on the flat line of V1, and then we can construct it by an inverse transformation, right? By using the reconstructed data formula up here, okay? So this isn't a case where we have a two-dimensional data set, okay? But you can, of course, generalize this to arbitrarily large data set, okay? So this is basically the entire process that we are going to do. We need to select the basis of for the dimensional space, right? So we want our data to be orthonormal, so we don't have any overlap or leakage of information from one dimension to the other. So we want to make sure each of the dimensions that we choose, you know, our VIs all the way down until Vn are orthonormal, right? They're orthogonal to each other, okay? So once we've done that, we found, for example, for each time we recurse, we find the direction left in the data set that displays the most variance, then we can use that as the ith dimension in our orthonormal projection. And then after we've done all of the selection, right, we've done this process of selecting all of the dimensions, then we can define a new center, right? The center is just moving from the space and then represent all of the data points in that new basis, okay? We don't have to use all of the dimensions here, right? We can use some of them and then strike out certain dimensions so that we can lower the dimensionality of the data set, okay? So instead of using n dimensions as in the normal size, right? Remember, n is the number of features, right? We're going to use k, right? K is the number of remaining dimensions, okay, that we're lowering to, okay? All right. So with this in mind, we can define one of the key algorithms, which is principal component analysis, right? It's basically the same idea of looking at these linear projections, okay? So we can take a large dimensional space into a smaller dimensional space, okay? There's, I think, some problem with the slide here, where we want to take something like what we've done just before, right? Project a 2D into a 1D space, or project a large dimensional space into a smaller one. So for example, if you did an NLP project or you know about NLP a little bit, you may have come across the idea of word embeddings. Word embeddings basically take a very large dimensional space where each dimension is a single word and tries to reduce it to a much smaller dimensional space, okay, where that dimensional space is quite dense. So that's the idea behind embeddings as well. It does it in a different process, but it's similar, okay? So again, what we want to do is, as it says here, is project and find the V with the minimum least squares reconstruction error, okay? Depending on how many dimensions we're using, right? So it depends on the K that we have here. So we want to choose the V dimensions that minimize the residual variance, right? And in order to do that, obviously, every time we choose a new component of V, a new dimension within the V of the K components, we want to choose whichever dimension is maximally displaying variance from the remaining data set. So you can think of this as a iterative, greedy algorithm that we might want to do in order to compute the minimum least squares reconstruction error. Okay, great. So you can see this process at work in this animated GIF. You might be able to see this from a number of sites, right? The idea is that we might have in this two-dimensional space, if we want to reconstruct the points accurately, we obviously need both dimensions, right? So depending on whichever basis that I choose here, you can see the gray windmill, so to speak, is basically a set of orthonormal vectors, right? They're at right angles to each other. And any one of those choices in any degree can perfectly reconstruct the data set. Okay, but the question is now we want to throw away one of these axes, right? We want to throw away the minor axis, which is the light gray one. Okay, and that can be done by just removing all of the information from it, right? So we just discard it. The only way that we can save enough of the data is to make sure that the residual squared error is minimum. And you can see how that works here is that once we come to something like this point here, you can see the data set is all clustered around this. Sorry, let me do that again. It would be clustered around this axis right here, okay? So when you have that type of projection, it's all the data points are getting stuck on that axis, and you're losing a lot of data because all of the red line segments that are along are not being represented, right? On the other hand, when we choose something that's congruent with the pink line, right, the pink line segment here, okay, this is the best that we can do because the minimum distance for each of the red lines is smallest, right? So the squares are smallest, and you can see it represents the data set as best as possible because it selects the direction of highest variance. Okay, so that's the idea behind that. Okay, so we already know how we can represent the point exactly, right? If we go through all dimensions all the way to n, we'll get a complete reconstruction, right? But in any of these dimensionality reduction techniques, we don't have all of the dimensions. We just have a subset of them, okay? So we are truncating the n to a smaller number k, and we are trying to reconstruct the amount of loss from that. Okay. So then the idea is we want to look at the reconstruction cost, right? So the reconstruction is basically this formula here, right? Basically the idea that we have the actual data point. This is the ground truth, okay? True data point. Okay, and this is our approximated one, right? Approximated. Okay, and then when we expand out the terms, we can just cut it into two parts, okay? So when we do that, let's say we have the parts that are going from all the way from K1 to N, okay? So this is the entire data set, okay? And this part is the ones that we keep, right? The points that we, dimensions that we keep. Okay, so when we expand this out, you can see where we're going with this, right? Basically, this subtraction will only have a problem when we have cases of the dimensions that we didn't represent, right? We saved all of the dimensions 1 through k, so this term is fine, okay? So when we subtract these two terms from each other, we're going to end up with just with this term, right? Meaning all of the components from k plus 1 all the way to the nth. So the k plus 1 to nth minor axes that we decided to throw away because we're compressing the dimensionality, right? Okay, so then we can write it out like this. Okay, so what are we looking at here? Okay, again, this is the normal case where we have the outside sum over all of the data points. Okay, so we're now looking inside of the data set at all of the points that are in the data set that we didn't represent. And so we have two terms here. Okay, where we're looking at the terms where we have the vector times itself as an identity, right? And the case where we have covariance, right? So when the two vectors are not aligned, okay? But because we constructed, okay, this term, we constructed the vectors as a orthogonal, let's say, not orthogonal, okay? Then the covariance, there's no overlap between V and V of H and V of L, right? So they're completely independent of each other, okay? So we can say that in this case, it's a 0, right? So this term is going to drop. We don't have to worry about that. That's the nice thing about using an orthogonal basis. Okay, so we are just left with the term in the center here that we need to care about. Okay, so we can do that very easily, right? We're just looking at these cases here, where we're looking at the reconstruction cost of each of these individual items, right? So here again, we're looking at the cost of the squared cost of each item for all of the dimensions that we've dropped, right? Okay. So I think the only thing here that we've done on the first line is just transpose, right? Transpose the equation here, right? So we took the m data points and substituted on the other side because they're both summations. We can do that. There's no problem there. So we can just deal with the fact that we have all of these n dimensions on the outside and just consider the inside sum where we're looking at all of the data points. Okay, so we have the multiplication of these two inputs, right, which are our observations, right? But we've taken out the mean, right? We factored the mean out. Okay, so we are multiplying those together, and then we will get basically this part here, right? Where we have the diagonal sigma matrix, right? The identity matrix there, okay? All right, so good. Let's go on from there. Okay, so it says on the bottom of this slide, right, we have the eigenvectors that we want to calculate from the covariance matrix, right? So we can do this by using any number of different ways. One way that we're going to explain a while from now is to use singular value decomposition to do that, right? So we have this covariance matrix that's looking at the interplay between each of the dimensions and figuring out which ones are the most important. This is the part that gets us to choosing the dimensions that have the most variance per iteration, right? We can do this all simultaneously. Okay, so we end up with the eigenvalues over here. Okay, if you remember your linear algebra, right, you use singular value decomposition, you will get from the covariance matrix, you'll get a set of eigenvalues for each of the dimensions, right? The dimensions are specified by the eigenvectors of the covariance matrix, but the magnitude or their importance are going to be specified by the eigenvalues. Okay, so you can think of this as an operation that we can do on the covariance matrix that will get us all of these orthogonal bases that we want from all the rest of the information. Okay. Okay, so this is telling us what the reconstruction cost is for all of the endpoints over the dimensions that we decided to drop. Okay, again, these are the dimensions that we're deciding to drop here, which are the ones from k plus 1 to n, all of the remaining ones. Okay. Okay, so by doing this, we get a reconstruction cost that's minimized because when we do the eigen decomposition of the covariance matrix, right, we will get all of these coefficients. These coefficients will be ordered from largest to smallest, right? So we can just say, okay, we're going to retain lambda 1 all the way to lambda k, because these have the largest numbers on the covariance, the largest magnitudes for the eigenvectors. They're the ones that are most important. Okay, so the remaining ones that we didn't capture, which is lambda k plus 1 through lambda n, these are all going to be dropped. Okay, so basically, this is the reconstruction error that we have. Okay, oops, okay. Okay. So as a result, we can see what we're doing with this, right? When we think about what the data is represented by, okay? When we do something like PCA, basically we're saying that all of the data points can be thought of as normal distributions on a particular axis, right? So we have V1 and V2 here, okay? And we're representing them as on the covariance matrix, and we are thinking of them as normal distributions in both directions. So we have a normal distribution here, right, on this axis, and another normal distribution on this axis, right? And we're trying to capture that using the decomposition of the covariance matrix. Okay, so when we want to do take this covariance matrix and we want to express it as a matrix multiplication, right, then we're going to get this type of formulation, right, where we have the new vectors that we are trying to engineer on both sides, the V and the transpose V, and then we have the covariance matrix in the middle. Okay, that's showing us what to do. Okay, so when we decompose it, we'll end up with this formulation where we can write the covariance matrix in terms of the eigenvectors, right? So we'll get this formulation over here. Okay, and the important thing here is, again, once you've done the multiplication, right, you basically are just looking at this particular lambda, right? The lambda is again the eigenvalue that tells us how important is that particular eigenvector or that particular dimension towards representing the data set, okay? So you can see this here in this figure, right? So if we assume we have two Gaussians here, one, again, in the V1 space and another one in the V2 space, right? Basically, for the lambda 1, right, it's basically telling us how much space we have, what's the stretch of this Gaussian distribution to characterize the data set in terms of V1, right? So you can see the square root of this tells us the distribution properties for the data set in the V1 direction, and similarly for V2. So a smaller lambda, right, represents a less variance, right? So you can see here, again, we have the same signature that lambda 1 is larger than lambda 2, and that would recurse when we select additional dimensions for a larger dimensional data set. Okay, so that's the idea, right? We're going to start from a data matrix, right? We first need to move the origin to the appropriate place so that the origin of the new dimensions is at the center of the data. Okay, so we can either do that as pre-processing. Typically, that's what we do, or we can involve it in the PCA algorithm. Okay, so either way is fine. Many times, what you do is before you even call PCA, you subtract the center, right, the mean of the data, and then you can add it back in at a later point. Okay, either way, you need to make sure that PCA gets the data in the appropriate format. So either you do it before or afterwards. Okay. Also, what you typically do is you also scale the dimensions of each data set, right? So you can get things within a normal distribution, okay, and then it will help decorrelate the magnitude of each of the variables. Like you saw in the normalization lecture many weeks ago, if you have one particular feature that's ranging from 1 to 0 and another one that's ranging from 100 to 1 million, then be needing to scale both of these by its variance will help make sure that both have the same magnitude so that most of the algorithms that expect normally distributed features can work properly. After we've done this, then we can do the computation of the covariance matrix, right? Once we've computed the covariance matrix, then we can apply an algorithm, okay? We're going to learn one later. Just introduce it offhand. You're not going to need to solve it, okay? You're just going to assume it's a black box to find the eigenvectors and eigenvalues, okay? That's going to be singular value decomposition, okay? Which hopefully you've had touched on in your linear algebra classes, either 1 or 2. Okay, after you've done that, then you have this finished in the sense that you already have this set of dimensions that are linear orthogonal projection of the data into a new data space, a new dimensionality. But we have, importantly, the eigenvalues for them, okay? So that they've been selected such that the first dimension has the most representative value, right? Meaning it captures the highest variance in the data set. And the second dimension happens to be orthonormal to that and captures the second most large variance of the data set, okay? So all of this is ordered, right? So this happens after we do SVD, okay? And then we can just compute well, not even compute, just select the largest eigenvectors, okay, after that. And once we have that, then we're done, okay? All right, so now we'll move on to singular value decomposition. Again, one of the problems with PCA, if we do it the way that we saw on the previous slide, okay, which is just to compute the covariance matrix and find the eigenvectors and values, is this really only works well for square matrices, okay? But as you already know, in machine learning, we almost always have rectangular matrices, right? We often, especially with deep, big data, which is why we want to apply dimensionality reduction, right? We will have many more data points than we will have dimensions, okay? So using something like singular value decomposition is very useful, okay? So you can think about SVD as basically some type of transformation, okay? So that is just re-representing the data in a different space, okay? Which is basically a method of taking the data set and rotating it, scaling it, and then rotating it again, okay, to achieve the same output. Okay, so we want to go from this representation over here initially to this representation over here as the final one for representing the data. And we can do that by any means, right? So we can follow these 3 steps to do a scaling as well as 2 rotations to represent that data. Okay? Okay, actually, I think I highlighted it wrong. It's supposed to be here. So we do the rotation, right? And then the scaling, uh, and then another rotation. Okay, so we want to represent the data on a different axes, right? So the axes are here, as opposed to the original ones that we might have in the yellow and red. Okay, so with a lot of these types of matrix factorization approaches, the idea is very simple, right? We take an original matrix that we have, so our data matrix X, and we just write it as a product, right? A matrix factor, matrix multiplication of several other matrices, okay? And basically after that, we can recover the original matrix, right? So we're just going to write X as a product of three matrices, okay, a weight matrix, a singular vector matrix, the U and V, and then a singular value matrix, right? Here, it is a diagonal matrix, right? So a matrix like this, okay, it's a square matrix, where on everything off the diagonal are all zeros, okay, all zeros. And then the diagonal matrix will have the eigenvalues. So eigenvalue of 1, eigenvalue of 2, eigenvalue of k. Okay. Well, I shouldn't write k. I should write n here because later on we're going to truncate that. Okay, so I'll write n. Okay. And that's where we're going with this. Is if we can write it in this format, it'll be very nice because as you already heard from before, what we're going to do is truncate this singular value matrix. We're going to throw away parts of it, right? So we'll say, okay, this stuff over here, all of the components that are downstream, okay, the components here, okay, this block here, which is from k plus 1 all the way to k, sorry, not k, all the way to n, okay? We no longer want them. We want to reduce the amount of data, okay? So we're going to start with this, right? We have the weight matrix. Again, one row per point, okay? It corresponds to where this particular example is in the new space that we're representing, okay? Our singular matrix, right? It's called singular because, again, we only have one entry on the diagonal for each point, okay? And then our singular vector matrix, right? This is basically the expression of all of those v vectors that we saw earlier, right? So for example, when we had this x1 and x2, right? Okay, then this value here, v1, would be encoded as in this each row here, right? Because we have k of them that we're going to eventually save. Okay, so we're going to start with possibly all n of these, okay, and then reduce it to k, okay, so that we have a smaller number. Okay, so that's the idea behind this. If we did it at full rank, okay, which we would have in the case, then we would have a larger number of points. I think this slide is still not quite correct. So I think you can ignore the diagram here. This is still, I think, a bit problematic. Okay. Anyways, the important point that we want to think about is just basically using SVD as a black box. Okay. So once you have learned the SVD algorithm from linear algebra, it's basically used to accomplish the principal component analysis. Okay. So the core part of the algorithm is just to call SVD, right, on the rescaled and centered data set, okay? And then ask for basically not to reconstruct the entire data set using all n dimensions, but use a subset, right? The first k singular vectors, all right, that can use this, okay? And then we can derive these coefficients directly from the matrix, right? Or we have a weight matrix times the singular value matrix, and this will get us what we want. to create the new vectors, right? Okay, so this is now the new approximated x that we have derived by using up to only the kth component in the space that we've reconstructed. Okay, so that's the idea behind PCA, is to look at the data set, find in the data set the directions of the highest variance, capture those iteratively, okay, through each dimension by using orthonormal bases, and then use that compressed representation to reconstruct the data set with as minimal loss as possible. And this is, you know, just basically a quality, a characteristic of, you know, singular value decomposition, such that you will always get the the weight, the eigenvalues, the eigenvalues of less important ones at lower ranks, okay, because all the eigenvalues on the diagonal matrix are ordered by their magnitude. Okay, so let's take a look now at the point on PCA. Okay, so let's see. Can I make this a little bigger? Okay. Sorry. So there was a period in machine learning and in a lot of representation work where the idea is that you would use eigendecomposition to reduce data from any domain into something that can be operated on using traditional machine learning by using PCA first. Okay, and one place where it was applied very successfully was on face recognition as well as face representation. Okay, so in the 90s, in the early 90s, researchers at Microsoft started off with the idea of using eigendecomposition using PCA to represent faces. Okay, so we can think of these faces again as a vector of pixels, right? And what we want to do is reconstruct them using a set of vectors, right? That are basically images in themselves, right? So we take the entire picture here, right? We run it through PCA to find the singular value decomposition, okay? And we take each of the rows in VT, okay? Which are, again, vectors themselves of up to up to n, right? They're the same size as the original features, okay? So you can see that they actually reconstruct an entire image face, okay? So the first thing we need to do is like center all of the data. So we have all of these faces. We're going to average them out, right? And this is what an average face looks like, right? In this grayscale data set. So it looks pretty like a blurred image of a face. It's quite symmetrical, right? And what we're doing is then saying that all the other faces in the data set are basically this average face plus some linear component of some remainders, okay, the variances in these other dimensions, right? So this is one dimension where if I add the mean face with some linear weight, right? Some weight of this V vector, I will reconstruct each of these faces with some fidelity, okay? If I'm allowed more than one dimension, okay, more than one vector here, and then accordingly more than one singular value, okay, let's say I get 2, then I will have another weight here, which would be on the U matrix, right? Which would help tell me how much proportion of V1 and V2 do I need to add together to get each of these faces again over here, okay? So you can see that basically at any one point, okay, I can truncate the number of dimensions that I'm using here or over here, okay? And then just saying that I'm going to represent each face with as many components as I have that I'm allowed to do. Okay, you can see, for example, this first one is adding a wider face. This one is adding light towards the left side. This one is somehow darkening the face. Okay, so all of these different components are being added as what do I say? Orthogonal basis of choosing the best way to represent faces. Okay, so you can see this. You basically are looking at these two faces, this one, this lady, and this man, and we are showing you what happens when these two faces are reconstructed using different k, right? So here, when I only have 4 dimensions, meaning I just have the average face plus the 4 first eigenvectors for the faces, I can reconstruct this face to look as close as possible using this. All right, so it doesn't look very close yet because I don't have enough components. But gradually, as I tune up the number of k that I have, then I can accomplish faces that look more realistic. Okay, and similarly for this women's face here, using 4 dimensions and 50 dimensions. Okay, and so again, you're looking at a fairly a large dimensional image here. Maybe this is again 256 or something like this. So we've lost a lot of dimensions, right? We're only using the k1 through 50 to represent on these two bottom ones. Okay, so it's helpful to know a little bit about the relationship between SVD and PCA. Okay, so when the data is centered or mean of 0, then PCA and SVD all do the same thing. Okay, the important thing is that SVD doesn't necessarily need you to compute the full covariance matrix. Okay, so that's very important. Okay, I'll answer your question in a second. Okay, so we can ask SVD just to generate a certain number of coefficients, right, our eigenvalues, and then stop there and then use that to represent the data, right? And it's also the case that in other forms of PCA, you might need a guarantee of a square data matrix. So this is why SVD is the preferred avenue to use to accomplish PCA. So we use SVD pretty much all the time for PCA because, again, you don't need to compute all of the covariance matrix, okay? You can just compute as the approximation to whichever rank you want, and then it doesn't require a square data matrix, okay? So how do we decide how many components we want, okay? So this is a great question. We always want to try to present the data with as high fidelity as possible, but we have to decide what amount of loss we want. So typically what we can do is we can graph the reconstruction loss, this J reconstruct, right, that we talked about earlier, okay, and look for an elbow. There's no real scientific way to do this, okay? So if we think, you know, if I have the full rank of the data, if I use all n dimensions, there'll be no loss because I can factorize completely, I can recover everything, right? If on the other hand, I use only 1 dimension, there'll be a very large amount of loss, right? So, you know, this is the reconstruction loss on the y-axis, right? So as I gradually scale up the amount, then I might see the reconstruction loss come down. But at some point, it might saturate. It might say, okay, even though I have more dimensions that I can add in, I'm only going to get small amounts of utility from this. Because remember, the dimensions are ordered in terms of the amount of variance they have, okay? So we can look for something like an elbow, okay? And say here, all right, it seems like we've really run out of utility. You can think of it sort of like SVD, like SGD, where we're looking for, you know, basically a very flat gradient, right? When we say the gradient's not moving a lot, then we can say we finished learning, you know, tuning a little bit more might help, but it might overfit, okay? So when we have represented as much data as we want, then we say, okay, we cut there, and then we'll use this point and say, okay, that's enough. We are going to use that K, okay? So Another algorithm that you need to know about for unsupervised learning is obviously clustering. I mean, if you go to a grocery store and you look at fruit, you might see the image on the left, and we know what these are, even though we might not be able to give them names. So you can think of a toddler walking into a store and seeing all of these different fruits and not being able to tell what types of things they are, but they obviously they can distinguish what these are, right? Say, oh, there's some hard fruits that are green and some, somewhat softer, spongy looking fruits that are orange, okay? And then be able to distinguish it in this way. Okay, so that is the idea of clustering, right? A clustering is just basically a collection of points. We're going to say that a K cluster partitions the entire data set into a number of K clusters, right? Where the membership could be hard, meaning that all of the points need to belong to exactly one cluster. There is no intersection between clusters, okay? Or we can also have a soft clustering, which we'll get to later, right? So the soft clustering means exactly the opposite of this, that there can be some overlap, okay? And that points probabilistically belong to a cluster, right? They might belong to multiple clusters. They might actually belong to every clusters with some non-zero probability, okay? And that each cluster has a unique center, a centroid K, right? So some mu for that particular cave cluster. Okay, so if we colorize the data set here and we ask for maybe about 10 clusters, maybe our clustering algorithm, if given a data set with only these two dimensions, x1 and x2, would output something like that. Okay. So this comes back to one of the other questions that Ching Han asked earlier, which is like, how do you determine where to stop? Okay, so let's think about this. So again, we're going to have a loss function, okay, that we're going to think about. All right. So we want all of the points in some way to be similar to each other, right? So that's what a cluster means, right? They have to be points that are close together, okay, close to each other and to the center of the centroid, right? So we can think about trying to minimize some form of this, right? So we can say the error for a particular cluster is looking at all of the data points, okay, and seeing how far they are away from the center, right? And if I square that using an L2 idea, right? So I have a squared penalty, then the farther away from the center you are, the worse it gets, right? And quadratically so, right? Okay, so you could use any other form of measurement for error, but this is the general idea. Okay, and when we think about doing the clustering error, it's just computing these component ones over the entire data set. Okay, so the problem of this is minimizing this is a greedy problem. Why is that? Because again, this is a hard clustering assignment, so things can only belong to one cluster point. Okay, so it's not a continuous um, uh, problem, right? It's discrete. Either a point gets assigned to one place or the other, which means it's hard for us to optimize. Anything when you have a max or min, you already know we have problems optimizing. Okay, but we can find simple and good solutions for that. Okay, so the one algorithm that you need to be familiar with at this point, which we're going to get into in the later half of the lecture, is k-means. Okay, k-means starts by declaring randomly centers. Okay, so here we're going to say we are going to use k equals 2. Okay, so we want two clusters from this. So we're going to randomly initialize the starting point of the two clusters. Okay, and then we're going to iterate. Okay, the first thing we're going to do is in k-means is estimate the membership of points to clusters, right? So we have these two cluster centers, right? One red, right, and one blue. Okay, and we're going to ask for every data point out there. Okay, let's say this data point over here. Which center are you closest to, right? Are you closest to this one or maybe closer to this one, right? And depending on which side it lies on, I'm going to assign it a color, right? Belonging to a particular data point, particular centroid, sorry. Okay, and as you can see here, that obviously it defines a hyperplane separating the two, which is the same as we have seen before, which is just looking at the perpendicular bisector between the two centroids here, and then cutting the data space in half, right? It's a hyperplane separating the data space. Okay, once we have that, we're going to reuse those partial temporary memberships to recalculate the cluster centers. So I'm going to look at all of the data points, okay, that are blue. Let's say, can't draw it very well here, but let me just take the pen instead. Okay, and then say for all of the data points that are blue, if I think of them as all equally important because they're all cluster members at this point, can I average all of those out and determine a new center? Okay, so that's, you can see the center has shifted from somewhere here to over here, and the red one hasn't shifted as much because you can see there were more points over here than out here, so it's shifted slightly to the right. Okay, so once we recalculate cluster centers, well, then maybe we need to recalculate membership, right? So I'm going to recalculate the membership, again, looking at the perpendicular bisector between these 2 points, right? And then carving the space into 2 parts using the hyperplane, and then reassigning the points, right? So we can do this a number of times until we finish and have hit to convergence, right? Okay, so now we have 2 points, 2 cluster centers, and the cluster memberships look approximately quite good. Okay, so this is the idea of k-means, right? That's actually a very simple algorithm. It's going to lead us to the idea of expectation maximization in a short while, where we want to go through all of the clusters that we have decided to create. Again, you might be thinking, okay, how do I determine how many clusters I want to build? And again, we're going to use this idea of the elbow method, right? Look for some idea where adding a particular centroid adds some type of value. We can represent our data better with an additional cluster. Okay, like the data set that we just saw doesn't look like it belongs to 3 clusters. It looks pretty good with 2. It certainly doesn't look right with 1 cluster, okay? Okay, let's say we've decided the number of k, okay? So what we're going to do is follow the initialization. The initialization says I'm going to start, oops. Yeah, I'm going to start by picking a random location, okay? So you can do better than this, okay? This is just basically the simple algorithm, okay? We're going to start at some random location for all of the centroids, right? And then I'm just going to go through this loop, right? This loop basically says, for a number of times, I'm going to repeat this until it's converged, all right? I'm going to first assign examples to a particular cluster, right? So I'm going to say that that particular point, okay, xj, belongs to cluster y, whatever y is, okay? So it belongs to cluster 1 or cluster 2, okay? I do this by just trying to choose the y that minimizes the distance between the current cluster centroid for that particular cluster, right? And the data point, right? Once I've done that, I have to do the re-estimation of the center, right? The center is basically very simple to calculate. I have all of the points that I have decided, right, over here. Okay, and then I'm just going to sum them all together and decide a new position for it by dividing through. Okay, that's going to build the next position that I'm going to look at, right? So I have a new cluster center, a centroid for that particular cluster. Okay. Okay, so I keep on redoing this calculation over and over again until I've decided that the cluster membership isn't changing. Okay, and then I return the set of memberships for all of the points. Okay, so we can actually show very easily. I won't spend a lot of time on this because, again, we are already past the hour mark. Okay, to show that these 2 steps, basically the cluster membership step and the recomputation of the mean step, has to converge. Okay, they can only decrease the error that we have, which we call J clus, right? J clus, remember, is a sum over individual errors for each cluster, right? Where the error for a cluster is basically the sum of the squares or any other distance measure between a point in the cluster to its center or centroid, right? So at the beginning, we're going to start with a value that is some arbitrary amount, okay, not arbitrary, sorry, an amount that's dictated by the initialization, okay? It might happen that we start with a clustering that has no error. You can think about how that's even possible. What would that mean? Okay, and if that's the case, we're done. Otherwise, what we'll have to do is try to minimize it, right? And to minimize it, we are doing these two steps, okay? So we first are going to make sure that we choose a new centroid, okay, that is going to improve upon the one at the last iteration, right? So this was our center at the last iteration. And this is our new mean, right? New centroid. Okay. And then the second line is what we're checking is that because when we calculate our new centroid, it's always calculated as a mean of all of the points. There is no way that we can actually increase this amount, okay? That by calculating a new cluster center to be the mean, there is no way we can make the mean squared error to go up, okay? So we can see this point here, right? Why would it be the case that when we use a new cluster membership, it's going to be better than the previous one? Okay, why is this always true? Right? Why would that be the case? Okay, the only reason why the cluster center would change from t plus 1, sorry, t minus 1, okay, from t minus 1 to 1 is because we switch membership to a new center, and the only way we do that is because the distance was made smaller, right? So there's no other way that that could happen. Okay, so this is always going to be true, right? That's the idea behind that. Okay, let me see. I need to clear the annotation. All drawings. Okay, good. Okay, so we have these two criteria, and for the reasons that I've just shown you, that will always be the case, that these two steps will always either stay the same or be minimized, right? The first one is, again, because when we change the cluster center from t minus 1 to t, the only reason why we do that is because the distance is going to be smaller or smaller than the previous. And the second one is because when we calculate a new center, it obviously has to be the mean of the distribution, which is by definition going to minimize the mean squared error. Okay. All right, let me see. Okay, back. Okay, so yeah, we've already gone through this. Okay, so I think you get the point here, is that we're always going to go through each cluster and then choose a way to make sure it is going to decrease the cost of the cluster. So we've actually outlined this, right? Okay, so I'm not going to discuss this in much detail. You'll see this narrated in your tutorial for this week. Again, this week's the tutorial for unsupervised learning will be recorded. I think our TA Martin is recording this, and so you can follow along if you're not clear about the math in this part. Okay, now there are some particular problems with k-means, and you can think about where they could come from. Okay, Mostly it's about initialization, okay? Because if you initialize your clusters at different positions, you might get different results, okay? So one of the things that we try to do is to initialize in a way that is not so terrible, okay? Because if, let's say, we choose all of the clusters to be initialized at point 0, then we have a big problem, right? Because they're all sitting on top of each other. All the cluster centroids are sitting on top of each other. They're not differentiable from each other, so they're all going to move in the same direction. Okay, so we need them to be different from each other. And so one way we can do this is to make sure that we try to spread out the clusters initially. So what we can do is, again, take a greedy algorithm, okay, where we first pick the first point at random, like it says, okay, but then all of the other subsequent points, okay, we are going to pick by looking at all of the possible points and choosing the point that's farthest away from any of the remaining centers. Okay, so if I've already chosen 5 centers, 5 points to use as the first 5 cluster centers, and I need to choose the 6th one, I'm going to choose the point that is farthest away from wherever those 5 other points are. Okay. So this is good. It spreads out all the points to be as far away from each other. But one problem is that it is still deterministic after the first point selection, meaning that after you pick the first point, there's no randomization that's being involved here. Okay, so what we might want to do is make it a little bit more stochastic. So there's an algorithm that you actually have access to right away through sklearn. So when you use k-means in sklearn, this is actually what it does. It uses this k-means plus plus algorithm, okay? So when you select a cluster centroid, basically you choose the point at random, but in probability, proportional to the square distance of the remainders, okay? So it's the idea that we just saw, okay, in the furthest first heuristic, but it doesn't make it deterministic, right? It basically says, I favor points for additional clusters that are far away from existing clusters, but I'm not going to demand it. I'm going to make this a soft constraint, which I'm going to just probabilistically weight points that are farther to be better. Okay, so I choose the point at random, but in probability, proportional to the squared distance from all of the other clusters. Okay, so you can see this here. I first have to assemble what are the distance thresholds, okay, for all of these different parts. And then I have to normalize it, okay, by dividing through all of the distance measures, right? And then I'm going to choose the cluster centroid for that. Okay, then after I do this, I can run k-means as per usual. Okay, let's see, we had a comment there. So can clustering be used in NLP? Yes, we can definitely use clustering in NLP as well. Word vectors are by nature constructed such that they are already obeying something like the PCA property, where they spread the signal evenly throughout all of the dimensions. So, you know, you probably get very limited value for something like word embeddings, right? When we construct word embeddings, we set the k specifically such that we can spread the amount of information over all of the k components. Okay, so choosing k-means to then cluster the words within the centroids are probably not going to have as much a good effect, but it can be done, definitely. Yes. All right, so we come back to this point that Cheng-Han mentioned earlier, that you know, how do we decide how many components in SVD to choose, PCA to choose, or in k-means, right? So we can say, well, I can choose a very large number of clusters or very few, okay? So the question is, do I add another cluster or not? So this is a recursive formulation, right? So I have, let's say, k clusters already. I want to decide whether I want to add another one or not, okay? So one of the big deals is thinking about the J-clust algorithm, error function, right? The error function of J-clust basically says, I'm taking the sum over all clusters, okay? And looking at the amount of, you know, infidelity there is to representing each cluster using just its center, right? So if I represent each point with its center, how much is the squared loss for each point? Okay, so there's a quick question that I want to poll you all on since you're all here. Okay, so you can choose, let's see, check, sorry, I'm using the wrong pen here. Okay, check yes if you think this is the case. Okay, X for this, or you can use teacup for this one. Okay, so if I use J class as a fitness measure, why isn't it any good? Okay, is there a reason why this is not going to be a good solution? Okay, so I'm going to have to find a poll. Let's see, can I find a? Okay, so I need to see the participants list here. So you can go to your participants panel, and then, sorry, let me take off the annotation here. Okay, and let me know what you think. Is it because of the first criteria, the second criteria, or the third criteria? Okay, so most of you have voted. You mostly think it's the third one for each point. So let's take a look at that. Okay, annotate. I'm gonna throw away the annotation for a second. Okay. Because yes, we're going to end up with M clusters, one for each point, right? Because each cluster will be its own cluster center, so there will be no problem with any error. It'll be perfectly represented, but it's not actually doing any work, right? Because basically you're not clustering, you're calling every point its own cluster. Okay, so there is a big problem, right? We can't use that type of method to do things, to define a clustering method. Okay. I want to get back. Okay, yeah. So what we want to do is, again, use some type of elbow rule to say that, the more that we choose clusters, somehow the less utility we get. One way to do this is to regularize, right? So we all know what regularization means. It means taking the model and trying to try simpler fits, okay? By simpler here, we mean using less components, right? Because obviously if you have less components, you'll lose more in the representation, but somehow your hypothesis that you have, your model is less complex because it's losing some information, right? It doesn't have to represent another cluster centroid. Okay, so there are two different methods for doing this in k-means. They're both used quite equally. There's not a lot of guidance about which to use, okay? Basically, you can use the BIC or the AIC criterion. And basically, they're basically variants of just the last component. This is the regularization term, right? So the component on the left is the normal thing, right? Where we want to lower the amount of cost that we have in creating a clustering, but we're going to penalize how many clusters we use, right? So one of them is a linear penalty, right? This one here, which basically says each time I add another dimension, I'm going to cost extra component in n. Okay, so when I have large dimensional data, because n is the dimensions, right, then I'm incurring a linear penalty there. Okay, the Bayes information criteria penalizes just by log n, so there's no real difference in looking at the coefficient in the front, so you can ignore